Welcome, fellow dreamer. Tonight, I invite you to join me on a quiet journey through one of the most secretive and world-changing chapters in modern history. To walk beside me through a day in the life of the minds behind the first atomic bomb. Together, we'll step into the guarded deserts of New Mexico, wander the labs of Los Alamos, and listen in on the calculations, uncertainties, and quiet tensions that surrounded the birth of the nuclear age. This is a story of science, secrecy, and unimaginable consequences. A glimpse into the world of the Manhattan Project, where some of the greatest minds of the 20th century worked behind locked doors, racing against time and possibility. Before we begin, take a moment to dim the lights, settle into a comfortable place, and let yourself drift into the quiet intensity of this hidden world, where brilliance and burden walked hand in hand. I created this video to help you relax, unwind, and gently fall asleep while reflecting on the people and moments that shaped the course of history in ways still felt today. And, as always, I'd love to know, where in the world are you listening from tonight? Let me know in the comments. It's incredible how these stories continue to connect dreamers around the globe. And if you enjoy this quiet journey through the past, don't forget to like this video, subscribe to the channel, and tap the bell icon so you'll always have a place to return when you're ready to fall asleep to the stories of history. Now, close your eyes, take a deep breath, and let our journey into the dawn of the atomic age begin. In the closing months of 1942, as World War II raged across continents, a quiet urgency took root in a place far from any battlefield. It began with a letter, sometimes hand-delivered, sometimes cryptically worded. A letter that informed its recipient their skills were required for a classified government program, and that their cooperation was not just expected, but essential to national security. The idea was simple in its ambition: to harness the power of the atom to create a weapon so powerful it could end the war. The Manhattan Project, as it came to be known, had no official headquarters at first. It was an idea before it was a place, a constellation of initiatives, scientists, and engineers pulled together under a veil of secrecy, initiated under the direction of General Leslie Groves of the U.S. Army Corps of Engineers. The program had begun to grow legs by late 1942, aided by the scientific insight of physicists like J. Robert Oppenheimer, Leo Szilard, and Enrico Fermi. It had begun as a series of scattered efforts to understand nuclear fission and determine whether a chain reaction could be sustained and, crucially, weaponized. Early hints of this possibility came from Europe. In 1938, Strassman had discovered that bombarding uranium atoms with neutrons caused them to split and release enormous amounts of energy. The implications of this discovery were immediately apparent to theoretical physicists, especially those who had fled Nazi Germany. By the time Albert Einstein co-signed the now famous letter to President Franklin D. Roosevelt in 1939, warning of Germany's potential pursuit of an atomic bomb, the race had unofficially begun. What started as theoretical models and university experiments now demanded physical space, military funding, and absolute secrecy. Scientists who once taught classes in thermodynamics and quantum mechanics were suddenly issued clearance levels and asked to abandon their posts, pack up their families, and vanish from public life. Their destinations were vague. The project's front organizations, obscure Army engineering units, and shell companies gave little indication of what lay ahead. At first, the research remained centered in places like Columbia University and the University of Chicago. At Columbia, physicists worked feverishly to understand how uranium-235 could be isolated from its more stable sibling, uranium-238. The process was tedious, involving massive, inefficient machines known as cyclotrons and calatrons, but it was essential. Only a tiny fraction of naturally occurring uranium, less than 1%, could undergo the kind of fast neutron-induced fission necessary for a bomb. The rest was inert for those purposes. In Chicago, meanwhile, Enrico Fermi had set up his own experiment, one that would come to mark a monumental moment in scientific history. Fermi and his team constructed a makeshift nuclear reactor out of graphite blocks and uranium. On December 2, 1942, they achieved the first self-sustaining nuclear chain reaction in human history. The team monitored neutron levels carefully, inching toward criticality with exquisite caution. When the reactor went critical, Fermi simply stood back and nodded. "The Italian navigator has landed in the New World," the coded message read. With this success, the theoretical had become practical. A controlled chain reaction was possible. Now, the question shifted from "can we do it?" to "how fast can we build a bomb?" That urgency coincided with Grove's decision to centralize the sprawling operation. Security concerns were mounting. Too many scientists knew too much. Too many locations were exposed to casual inquiry, and the timelines were tightening. A single, remote, tightly guarded site was needed where the final stages of design, construction, and testing could be overseen without interference. Los Alamos, New Mexico, was selected. The site was remote, high in elevation, and far from prying eyes. Formerly the location of a boys' boarding school, the mesa was quickly repurposed. Roads were built, housing was hastily constructed, armed checkpoints were installed at every entrance. The lab would be known only as Site Y for much of its early history. For those who arrived to work there, the address on letters home read simply, P.O. Box 1663, Santa Fe. In the winter of 1943, new recruits began arriving, and even artists and writers tasked with documentation and technical illustrations. Some knew what they were working on. Most did not. They were told only what they needed to know for their specific assignment. Compartmentalization was a founding principle of the project. It was safer that way. Those who arrived at Los Alamos found a strange mix of military regimentation and intellectual freedom. Armed guards patrolled the perimeter, while Nobel laureates scribbled equations on blackboards. Typewriters clicked away as reports were drafted, copied, and filed under layers of classification. Workers were assigned identification numbers and required to wear badges at all times. Even their spouses, many of whom had followed them to this strange outpost in the desert, were not told the full nature of their husband's work. In the early days, the atmosphere was tense but electric. Hitler's regime was known to have taken an interest in nuclear fission. The fear of Nazi Germany building an atomic bomb first was not abstract, it was real and terrifying. And so, the early stages of the Manhattan Project became not just an exercise in physics or engineering, but a moral race. They worked long hours, often 6 or 7 days a week. Progress was measured in calculations and prototypes, failures and revisions. Mistakes were costly. Radiation exposure, accidental criticality, or structural instability in reactors could mean disaster. Yet the work continued, and each breakthrough brought the team closer to the unimaginable. By early 1943, the three major arms of the project were in motion: uranium enrichment at Oak Ridge, Tennessee, plutonium production at Hanford, Washington, and weapon design at Los Alamos. It was the most expensive and expansive scientific enterprise the United States had ever undertaken, costing over $2 billion by the war's end and involving over 130,000 people. But for now, in this first year, there was only theory and preparation. The bomb was still a concept, one built of math, graphite bricks, uranium samples, and raw determination. And far from the headlines of the war in Europe and the Pacific, the Manhattan Project's architects quietly assembled the tools of something entirely new, the weapon that would split the world in two. The journey to Los Alamos was unlike any other. For the men and women summoned to join the Manhattan Project's core operation, the trip often began with vague instructions, cryptic train tickets, and military escorts who answered no questions. In most cases, even those traveling together weren't told where they were going until the last leg of the trip, if then. There were no guidebooks, no welcome signs, no maps. The only certainty was that their destination was remote and that they had been hand-picked for something vital. By early 1943, the U.S. Army had begun relocating scientists, engineers, technicians, and their families to what was then still called Site Y, a former boys' school high atop a mesa in northern New Mexico, at over 7,000 feet above sea level. The region offered geographical isolation, a cool climate, and natural barriers in the form of deep canyons and rugged terrain. More importantly, it offered secrecy. The remoteness of the site ensured that once someone arrived, they would not be casually leaving. Those who traveled west by train were often directed to disembark in Santa Fe, New Mexico, where they were met by military trucks or jeeps. Soldiers in plain uniforms with clipped speech and rigid posture conducted the final stretch of the journey. They asked no questions and answered none. The altitude could be felt in the chest, a tightness in the lungs unfamiliar to many arriving from the coasts. Dust clung to the tires and coated the boots of those who stepped out for the first time. What they found was not a state-of-the-art research facility. Not yet. In the early days, Los Alamos was closer to a makeshift village than a top-secret weapons laboratory. The remnants of the old Los Alamos Ranch School were still visible: rough wooden lodges, a handful of stone buildings, and a dirt road that cut through the middle of the compound. Construction crews worked non-stop to raise barracks, laboratories, mess halls, and water towers. The roads were unpaved, the plumbing temperamental, and the power unreliable. But the work had to begin immediately. Upon arrival, each person was processed by military personnel. Mail was censored. Phones were monitored. Even children were taught never to repeat what they overheard at home. New arrivals were struck by the contrast. On one hand, Los Alamos felt like a scientific summer camp: bunkhouses, shared mess halls, community dances. On the other, it was a fortress of secrecy. There were guards at every entrance, soldiers stationed at checkpoints, and constant surveillance, both overt and subtle. Visitors had to be pre-cleared by Army intelligence. A wrong word or suspicious behavior could result in immediate expulsion, or worse. Despite the conditions, a strange sense of camaraderie emerged. Everyone understood the stakes, even if they didn't fully understand the project's scope. Scientists who had once taught at Ivy League institutions now lived in crowded quarters and worked elbow to elbow with young physicists just out of graduate school. There were Nobel laureates and undergraduates, engineers and machinists, chemists and military men, all thrown together in a high-altitude crucible. They worked long hours, often starting early in the morning and continuing late into the night. Equipment was constantly being delivered and assembled. Vacuum pumps, cyclotrons, early computers, anything that could help them understand the nature of atomic fission and bring the theory of a nuclear bomb closer to reality. For some, the isolation was invigorating. There were no reporters, no press releases, no external committees to answer to. Others found the conditions claustrophobic. The confinement of the mesa, combined with the constant pressure of secrecy, weighed heavily. Families lived in assigned quarters, often cramped and hastily constructed. The weather could swing between freezing winds and dry heat. Supplies were limited, and morale was always a fragile thing. Still, the work progressed. J. Robert Oppenheimer, the theoretical physicist tapped as scientific director, quickly became the central figure at Los Alamos. Brilliant, enigmatic, and deeply respected, Oppenheimer was both visionary and taskmaster. Under his leadership, research was divided into divisions and subgroups, each focusing on a specific component of the bomb's design. Some teams worked on explosive lenses, others on neutron reflectors, and others still on triggering mechanisms. Each unit knew only what it needed to know. Only Oppenheimer and a small circle of senior scientists had access to the full picture. The bomb, they had decided, would be built in two main forms. Was relatively straightforward in design, though its fuel was incredibly hard to extract. The plutonium bomb, based on Pu-239, was more complex. It was this latter design, nicknamed the gadget, that would consume most of the lab's effort in the months ahead. Security concerns were constant. Reviewed correspondence and intercepted suspect packages. Even within the project, whispers of communist sympathies or questionable loyalty were enough to trigger internal investigations. No one was above suspicion. Not even Oppenheimer himself. Despite the pressure, the breakthroughs came. Bit by bit, the team at Los Alamos solved engineering challenges no one had faced before. They developed new materials, built custom devices to measure radioactive decay, and invented entirely new methods for precision timing and explosive detonation. Each success came with new questions, and every question brought new urgency. War was still raging. The clock was ticking. In the evenings, there were lectures and technical seminars, often delivered in makeshift auditoriums by scientists who had worked all day and would work through the night. The talk was dense with theoretical physics, nuclear chemistry, metallurgy, but no one ever mentioned the word bomb, not in public, not even at dinner tables. Life at Los Alamos in those early months was a strange blend of domestic normalcy and apocalyptic purpose. Children played in yards, surrounded by barbed wire. Scientists discussed neutron behavior over scrambled eggs. Husbands returned home with graphite dust on their hands, unable to explain to their wives what they had spent the last 16 hours doing, and always looming behind every calculation and conversation was the knowledge, unspoken but ever present, that what they were building had never existed before, and that once it did, the world would never be the same again. Inside the dusty laboratories of Los Alamos, the early months of 1943 were marked by an intense, methodical focus on a singular challenge: how to make the theory of nuclear fission into something real, controlled, and ultimately weaponized. Although a broad understanding of atomic energy already existed, the leap from fission reactions observed in laboratory beakers to an explosive device capable of destroying a city was enormous. It would require not just a mastery of physics, but an entirely new language of experimentation, one built through sleepless nights, untested ideas, and constant recalibration. The starting point, always, was fission itself. The word had entered the scientific lexicon only a few years earlier. In 1938, after the German physicists Otto Hahn and Fritz Strassmann had split a uranium atom and discovered that it released an immense amount of energy, their discovery had been largely academic until theoretical physicists, most notably Lisa Meitner and Otto Frisch, calculated the implications. They realized that if enough uranium atoms could be made to fission in rapid succession, the energy released would be catastrophic. This formed the basis for what became known as a chain reaction. At Los Alamos, the scientists began by building on this foundation. Chain reactions required two things: a fissile material capable of undergoing fission, and a design that allowed the reaction to proceed faster than it could dissipate. It was the first of many paradoxes the Manhattan Project would confront: how to sustain an unstable process long enough to unleash its energy, but not so long that it failed to reach critical mass. The lab's earliest test devices were small and controlled. Physicists like Emilio Otto Frisch and Rudolf Peierls spent long hours inside concrete-reinforced test bunkers, bombarding uranium and plutonium samples with neutrons to observe how they behaved. These experiments were not dramatic. There were no explosions, no blinding flashes. Instead, researchers used Geiger counters, ionization chambers, and cloud chambers to monitor particle behavior. They recorded the slightest upticks in radiation levels, looking for patterns that might reveal how a reaction could be controlled or triggered. One of the critical challenges was measuring neutron multiplication. If a fission reaction emitted more neutrons than it absorbed, the process could escalate. But if too many of those neutrons escaped, the chain would fizzle out before achieving anything useful. Experimenters began using uranium piles, stacks of graphite and uranium blocks, similar to what Fermi had built in Chicago, but more refined and better shielded. These helped researchers study the neutron flux within various configurations. Another key question was geometry. The shape of the fissile core could dramatically affect how efficiently a reaction proceeded. It became clear that a spherical configuration was ideal for promoting a symmetrical implosion, especially for plutonium, which behaved differently than uranium. But even this realization had to be tested and verified through countless simulations and physical models. They built mock-ups out of inert materials to study how shock waves and compression would affect the nuclear core. Many of these early designs failed, either structurally or mathematically, but each failure yielded data, and data was everything. Plutonium posed an even greater challenge. Unlike uranium-235, which could be assembled into a gun-type bomb by slamming two subcritical masses together to achieve criticality, plutonium had a tendency to undergo spontaneous fission. This meant that a gun-type design would likely cause a premature detonation, known as a fizzle. To overcome this, the team realized they would need to develop an implosion method, compressing a plutonium core uniformly from all sides using high explosives. The science of implosion was in its infancy. No one had tried to compress a metal using a perfectly symmetrical inward blast. It was like trying to squeeze a water balloon evenly from every direction without causing it to burst unpredictably. Physicists and explosives engineers began developing the concept of explosive lenses, carefully shaped charges that could focus a blast inward, like a magnifying glass focuses light. These lenses required exacting precision. Even a minor irregularity could result in asymmetrical compression, rendering the bomb ineffective. Engineers like George Kistiokoski took on the monumental task of developing these lenses, refining chemical compositions and configurations through trial after trial. In parallel, other groups worked on tamper materials, substances surrounding the core that could reflect neutrons inward and contain the reaction momentarily to increase yield. Materials like beryllium and natural uranium were tested, weighed for density, thermal conductivity, and neutron reflection properties. Metallurgists shaped tiny components with micrometer accuracy, polishing them to a mirror finish. Every part, no matter how small, had to be perfect. But beyond the physics and engineering, there was a persistent and growing concern: radiation. Many of the early tests were conducted with minimal shielding, as the long-term effects of exposure were still not fully understood. Some researchers handled plutonium and uranium samples with gloved hands, unaware of how deeply the particles could penetrate. Over time, the risks became clearer. A few workers began showing signs of radiation sickness. There were incidents, some minor, others alarming. One technician dropped a container of plutonium solution, causing a brief but dangerous spike in neutron activity. That accident led to new rules, stricter procedures, and reinforced containment systems. Despite these dangers, the work continued. The scientists were driven not by thrill or fame, but by urgency. The war cast a long shadow over every experiment. Nazi Germany's efforts remained a looming threat. Even if they were believed to be behind the Americans, the possibility that Hitler could acquire a nuclear bomb remained unthinkable, and thus had to be prevented at all costs. This urgency justified long hours, sleepless nights, and growing moral uncertainty. Morale was a strange mixture of camaraderie and anxiety. The scientists formed friendships, played music, hosted lectures in the evenings. But behind the small comforts was a deep awareness that their experiments were not ordinary. They were building something that had never existed before, something that could alter the trajectory of human history. By the end of 1943, many of the fundamental problems had been mapped, if not solved. The uranium bomb seemed feasible, though uranium enrichment was proving agonizingly slow. The plutonium bomb, however, had emerged as the greater challenge, and also the greater promise. With the Hanford site beginning to produce plutonium in small but growing quantities, Los Alamos doubled down on implosion design. The focus shifted from theory to engineering, from if to how. The early experiments had done their job. They had moved the project from speculation to construction. The data had coalesced into designs. The labs now buzzed with plans, blueprints, and prototypes. The word gadget was starting to appear in documents, an innocuous name for the most dangerous object ever conceived. And still, beyond the locked doors and concrete bunkers, the world remained unaware. By early 1944, the Manhattan Project had taken on a more definitive structure. What had begun as scattered experiments and theoretical research now resembled a complex, fully integrated operation. At its heart was Los Alamos, the secret laboratory in New Mexico, where engineers, chemists, and theoretical physicists worked under armed guard to complete a weapon no one outside their classified world could imagine. But assembling such a diverse, brilliant and ambitious team had not been easy. In many ways, the interpersonal dynamics among the project's scientists were as volatile as the radioactive materials they studied. The man tasked with balancing these competing personalities was J. Robert Oppenheimer, a theoretical physicist from the University of California, Berkeley. Oppenheimer was chosen to lead the scientific direction of the Manhattan. General Leslie Groves, the project's military overseer, had seen in Oppenheimer a unique combination of intellect, charisma, and obsession. He was not an easy man to work with, but Groves trusted his capacity to lead some of the greatest minds of the era. Oppenheimer's style was cerebral and intense. He had an uncanny ability to absorb new information quickly. The scientists he brought to Los Alamos came from vastly different backgrounds. Jewish émigrés fleeing Europe, young American physicists fresh out of graduate programs, seasoned veterans of academic research, and engineers more comfortable with machines than with theory. Each came with their own vision of what science meant and how it should be practiced. Leo Szilard, one of the first to conceptualize the chain reaction, was meticulous and often skeptical. Enrico Fermi, known for his pragmatic brilliance, approached problems with quiet focus and a methodical calm that contrasted sharply with the intensity of his colleagues. Edward Teller, brilliant but prone to conflict, pushed for a hydrogen-based superbomb even before the basic atomic bomb had been proven. Then there was Niels Bohr, the Danish Nobel laureate smuggled out of occupied Europe, whose deep philosophical concerns about nuclear weapons often set him at odds with the project's single-minded purpose. These men, and many others, converged at Los Alamos, where their work was broken into divisions. Engineers handled explosive lensing and fabrication, while metallurgists studied the behavior of uranium and plutonium under high heat and pressure. Each unit operated with relative independence, but their outputs were intricately interlinked. A failure in one group could halt the work of another. Oppenheimer held weekly meetings to keep the project's leaders coordinated. These meetings, often intense and occasionally contentious, were the only venue where different teams could share findings and frustrations. Scientists debated everything: the purity of plutonium samples, the reliability of detonators, the feasibility of certain lens configurations. The pressure was constant. Mistakes meant delays. Delays could mean the difference between winning and losing a race that most believed Germany had already started. To many of the younger scientists, Los Alamos was both exhilarating and suffocating. For the first time in their careers, they were surrounded by intellectual equals, free from the constraints of traditional academic politics. Yet the secrecy, the isolation, and the moral ambiguity of their task created a psychological burden. They knew they were building a bomb, but most had not confronted what that really meant. Some tried to ignore the implications and focus only on the science. Others could not help but question their role, staring out over the canyons in silence. Those closest to him described a man increasingly torn between scientific ambition and human conscience. Despite these tensions, the collaboration yielded results. The different teams began making breakthroughs. Engineers found ways to machine and assemble extremely reactive materials with microscopic tolerances. The project had reached a point where its success no longer seemed hypothetical. It was a matter of refinement. There were moments of levity. Evening lectures by visiting scientists, impromptu string quartet performances, and desert hikes provided brief escapes from the weight of their mission. Families organized holiday celebrations, and children played in fenced-in yards under the ever-watchful eyes of military police. Yet, beneath the routine of daily life, a silent intensity pervaded every hallway and laboratory. Everyone knew that what they were building would change the world. No one knew how the world would respond. As summer approached, Oppenheimer's team began finalizing the core design of the bomb. The divisions between the practical and the theoretical had begun to blur. Engineers were now solving equations, and physicists were working with machine tools. The gadget, as it was still euphemistically called, was taking physical form. With each passing day, the language of theory gave way to the language of construction. But the human dimension of the project never disappeared. Scientists shared rumors about the war in Europe, wondering if Germany had made progress on its own bomb. News from home, scarce and heavily censored, filtered through in letters and shortwave broadcasts. Some worried about family members overseas. Others feared what would happen if their work was discovered by Soviet agents. A few quietly wondered if it was right to finish what they had started. For all the brilliance on display, it was still a human endeavor, messy, conflicted, and bound by time, driven by urgency, belief, and perhaps fear of what failure would mean. They pressed forward together. In Oppenheimer's notebook, a single line appeared one night in early summer. "We have gathered the most dangerous minds in the world. May we remain wise enough to use them well." The team was built, the bomb was coming, and there would be no turning back. By the middle of 1944, the Manhattan Project had grown beyond the confines of Los Alamos. The scientific problems had not yet all been solved, but the time for theoretical delays was over. If a bomb was going to be ready before the war ended, or before the enemy built their own, it would require not only brilliant minds, but also an unprecedented industrial machine. This next stage of the Manhattan Project was no longer about chalkboards and particle detectors. It was about concrete, steel, chemicals, labor, and scale. The United States government launched the largest construction effort it had ever undertaken, all under the veil of top secrecy. Entire towns were built from scratch to house thousands of workers, many of whom had no idea what they were working on. The scale of the enterprise was staggering. At its peak, the Manhattan Project employed more than 130,000 people and cost over $2 billion, a figure nearly incomprehensible for its time. One of the first major installations was at Oak Ridge, Tennessee. Nestled in the hills and valleys of eastern Tennessee, Oak Ridge was selected for its relative remoteness, access to hydroelectric power, and transportation infrastructure. The facility was designed to enrich uranium, a process that required isolating uranium-235, the rare fissile isotope, from the vastly more common uranium-238. The two isotopes are chemically identical, differing only slightly in mass. This tiny difference made separation incredibly difficult, requiring enormous machines and innovative methods. 3 enrichment methods were pursued simultaneously at Oak Ridge: electromagnetic separation, gaseous diffusion, and thermal diffusion. The electromagnetic method, developed at the Y12 plant, involved using Calotron's devices that used magnetic fields to separate isotopes by mass. These machines were massive, expensive, and finicky. Hundreds of Calotrons were built and operated around the clock, often by young women hired from local communities. Most of them had no idea they were enriching uranium. They were told only to watch the dials and keep the readings steady. Gaseous diffusion, the most ambitious method, was housed at the K25 plant. This process involved forcing uranium hexafluoride gas through a series of porous barriers. The slightly lighter uranium-235 molecules would pass through faster, gradually separating from uranium-238. It was a slow, energy-intensive, and complex procedure. Building K-25 required miles of piping, precise engineering, and massive compressors. Yet the team pressed forward. Even if one method failed, the others might succeed. Redundancy was key. Simultaneously, thermal diffusion was tested at the S-50 plant, a facility constructed at lightning speed. It used temperature gradients to separate isotopes, though it was less efficient than the other methods. Still, in the eyes of project leaders, every additional gram of uranium-235 was worth pursuing. With the success of any one method uncertain, all three were pushed forward in parallel. While Oak Ridge focused on uranium, another facility, equally massive and mysterious, rose from the desert in southeastern Washington state. The Hanford site was built to produce plutonium-239, a synthetic element that could be bred in nuclear reactors from uranium-238. Unlike uranium-235, which occurred naturally in small amounts, plutonium could be manufactured in large quantities, provided the reactors were powerful and stable enough. Hanford's reactors, known as the B, D, and F reactors, were the first of their kind. Designed by physicist Eugene Wigner and engineer DuPont Company, they used graphite as a moderator and water as a coolant. The reactor cores were massive, hundreds of tons of graphite bricks arranged to allow for a controlled chain reaction. Natural uranium slugs were inserted into the reactor, where they absorbed neutrons and gradually transmuted into plutonium. The irradiated fuel was then removed, cooled, and chemically processed to extract the plutonium. This chemical separation, called the bismuth phosphate process, was dangerous, laborious, and highly radioactive. Workers at Hanford handled intensely hot materials using remote manipulators and operated behind thick leaded glass. Contamination risks were constant, and safety protocols had to be developed in real time. Even so, accidents occurred. Some workers received high doses of radiation without knowing it. Others fell ill from chemical exposure. But the plutonium flowed, and the yields increased. Transporting fissile material between these sites and Los Alamos required extraordinary security. Couriers traveled by armed convoy, always changing routes and identities. Very few people had clearance to even know what was being transported. An error could mean not just loss of the material, but catastrophe. At Los Alamos, the arrival of purified uranium and plutonium changed the tempo of the work. No longer limited to theoretical models or small test samples, the scientists now had real quantities to work with. Experimental bomb cores were assembled. Implosion lenses were tested using high explosives. Diagnostic instruments were refined to measure neutron flux, shockwave timing, and energy release. Each test provided vital data. Each experiment brought the bomb closer to reality. Across all locations, secrecy remained absolute. Most of the labor force at Oak Ridge and Hanford knew only that they were supporting the war effort. Some guessed the project had something to do with a superweapon. Others believed it involved radar, fuel, or medical research. Only a few at the top knew the full truth. The scale of this mobilization was unprecedented, not just in its complexity, but in its speed. Plants that would normally take years to build were completed in months. Equipment that had never existed before was designed, fabricated, and installed under wartime pressure. bureaucracy was minimized. Urgency was everything. The Manhattan Project had become a nation within a nation, its own rules, its own hierarchy, its own infrastructure. Still, even as material and components flowed toward Los Alamos, the challenge of integrating all these parts into a functioning weapon loomed large. The design had to be exact. The timing circuits, the explosive lenses, the initiators, the tamper, all had to function within microseconds. The bomb would be either a resounding success or a very expensive failure. There would be no second chances. By the end of 1944, enough uranium had been enriched at Oak Ridge to begin final assembly of a bomb. Plutonium from Hanford arrived in small batches, each gram worth more than gold. The scientists worked in round-the-clock shifts. Some became exhausted, others euphoric. A strange determination gripped them. The weapon was no longer a dream or a nightmare. It was becoming real. The world outside knew nothing of this parallel universe. Towns near the project sites continued their lives in ignorance. In Washington, D.C., only a small circle of politicians and military officials had any idea what was underway. To them, the Manhattan Project was a gamble, a secret card held in the hope of ending a brutal war. To the people building it, it was an engineering miracle, a moral dilemma, and an unprecedented race against time. The scale-up was nearly complete. The final phase, building the bomb itself, was about to begin. By the beginning of 1945, the effort at Los Alamos had reached its most critical and technically demanding phase. With fissile material arriving in measurable quantities, plutonium from Hanford and uranium from Oak Ridge, the focus narrowed from scientific theory and industrial production to the careful, almost surgical task of assembling the first workable atomic device. This device, nicknamed the Gadget, would not be the bomb dropped from a plane, but rather the prototype for the plutonium-based implosion weapon. It would be tested in the desert to determine whether this groundbreaking design could actually function. The name Gadget was intentionally innocuous, used in classified documents and casual conversation alike. But those involved in its construction understood its deadly seriousness. It was the culmination of more than 2 years of intense, secret work. Now, the question was no longer abstract. Would the bomb detonate as designed? Would the implosion work? Would the resulting chain reaction release the amount of energy predicted? Or would it fizzle? Or worse, misfire catastrophically? At the heart of the Gadget lay a sphere of plutonium-239, about the size of a grapefruit, but heavier than lead, shaped into 2 hemispheres. The plutonium core required precise machining to a level of tolerance never before attempted with such a reactive and dangerous material. The metal's radioactive nature presented significant handling challenges. Even small amounts could emit deadly levels of radiation. Scientists worked behind shielding, using remote tools, gloves, and heavily reinforced safety protocols that had been implemented after early, dangerous mishandlings. Encasing the plutonium core was a hollow shell of high explosives, but these were not ordinary charges. The design called for an implosion, a perfectly symmetrical inward blast that would compress the plutonium core to a supercritical state. Achieving this required the use of explosive lenses, a revolutionary concept involving carefully shaped charges that would detonate with precise timing. These lenses had to convert the natural outward force of a detonation into an evenly distributed inward pressure. A failure to do so would scatter the plutonium without triggering a chain reaction, an expensive and potentially lethal failure. Designing and assembling these lenses was the job of physicist Seth Nettermeyer and explosives expert George Kistiakowsky, among others. The development of the lenses was painstaking. Engineers had to shape explosives into lenses with extreme geometric precision. Each lens was made up of two types of explosives, one fast and one slow. When detonated simultaneously, the different velocities would produce a converging shock wave focused inward. Even the slightest imperfection in lens shape, placement, or detonation timing could lead to asymmetrical compression and failure of the device. To test these ideas, the team conducted a series of non-nuclear experiments called Rala tests, which used radiolanthanum as a tracer to observe the compression symmetry in high-speed photography and radiation detection. The data was invaluable, but the tests often destroyed expensive equipment and posed hazards to the test teams. Nevertheless, they provided the insights needed to fine-tune the implosion mechanism. The detonators themselves also presented challenges. Each of the gadget's 32 high-explosive lenses needed to detonate within microseconds of one another. This required the development of a new kind of detonator, an exploding bridge wire detonator, which used a small electrical current to vaporize a filament and trigger the explosive. These had to be tested repeatedly, often under field conditions and amid unpredictable variables, to ensure absolute reliability. Meanwhile, work on the internal components of the core continued. Between the plutonium and the tamper shell, scientists inserted a neutron initiator. This tiny device, nicknamed Urchin, contained polonium-210 and beryllium. When imploded, along with the rest of the bomb, it would inject a burst of neutrons into the compressed plutonium, ensuring a rapid and complete chain reaction. Designing the initiator required mastery of radioactive chemistry, precision timing, and containment, all of which had to function flawlessly under extreme pressure and heat. Because of the implosion bomb's complexity, the uranium bomb, nicknamed Little Boy, was given lower priority at this stage. Its simpler, gun-type design, which used uranium-235 to create a supercritical mass through linear acceleration, was considered nearly foolproof. The engineers at Los Alamos focused their attention and anxiety on the gadget, where every part of the design pushed the boundaries of known science and engineering. By the spring of 1945, the various pieces of the bomb were coming together. Machinists fabricated casings and alignment mechanisms. Engineers assembled timers, switches, and fail-safe interlocks. Chemists monitored the aging of explosive compounds to prevent instability. Physicists ran calculations day and night to predict the yield and refine the implosion modeling. Every component, from the plutonium sphere to the triggering circuits, was reviewed, revised, and retested. Security at Los Alamos intensified. Only a handful of scientists and military personnel had access to the full design of the bomb. The vast majority of those working on individual components still did not know what the final device would look like or what it would do. Meetings were held in closed rooms, documents tightly controlled, movement restricted even among the inner teams. The pressure of secrecy, combined with the technical strain to create a tense, often exhausting environment. Yet, in this pressure cooker of war, secrecy, and discovery, many of the project's members pushed themselves beyond their limits. They were aware that what they were building was not just a weapon, but the first of its kind. Some saw it as a necessary evil, an end to a war that had already consumed millions of lives. Others were beginning to express doubts, especially as Germany neared collapse, and the primary justification for the bomb began to evaporate. But none of this stopped the work. The bomb would be completed because that was the mission. Oppenheimer, as the scientific director, moved constantly between labs and meetings, tracking progress, offering advice, managing personalities, and sometimes simply observing in silence. He knew that the success or failure of the entire project now rested not on theory, but on engineering. He also knew the weight of what was coming. Though he rarely discussed it openly, he seemed increasingly withdrawn, haunted not by failure, but by what success would mean. By June 1945, a final test was scheduled. The gadget would be assembled in a remote desert location in southern New Mexico. Known as the Trinity Site, it was chosen for its isolation and flat landscape. A steel tower was erected, bunkers were dug, high-speed cameras and measuring equipment were brought in from across the country. The gadget would be detonated not as a battlefield weapon, but as a controlled test. Its success or failure would be the definitive answer to years of work, secrecy, and fear. Before it could be transported, the gadget was fully assembled at Los Alamos. Each part was double-checked. The plutonium core was fitted inside its tamper. The initiator was nestled into place. The explosive lenses were mounted with painstaking care. Timing devices and safety switches were installed. The finished product was crude by modern standards, with exposed wires, heavy bolts, and a spherical, utilitarian shape. But it represented the most sophisticated object ever built by human hands, an instrument designed to harness the power of the atom itself. On July 12, 1945, the completed gadget was loaded into a convoy and carefully driven through the night toward the Trinity Site, covered in tarps and guarded by armed soldiers. It traveled the quiet desert highways as the world around it slept, unaware that the most powerful weapon in human history was now only days from detonation. The assembly was complete, the test was imminent, and history, for better or worse, was about to change forever. In the early days of July 1945, the desert of southern New Mexico became the stage for an event that would alter the course of human history. The Trinity Site, a desolate patch of flat earth nestled between the San Andres and Sacramento mountain ranges, had been chosen for its remoteness and stark emptiness. Here, with no cities or towns in close proximity, the first nuclear device ever constructed would be tested. It was an experiment rooted in years of science, secrecy, and moral conflict, and its outcome was still uncertain. Preparations at the Trinity Site began weeks earlier. Army engineers and physicists from Los Alamos arrived with trucks full of equipment, diagnostic instruments, cameras, oscilloscopes, high-speed chronographs, and reinforced bunkers filled with sensors. A 100-foot steel tower had been erected at the center of the blast zone. It resembled a skeleton in the sand, and at its top, the assembled nuclear device, the gadget, would be hoisted and suspended. From here, the implosion mechanism would be triggered, and if it worked as designed, the resulting explosion would mark the release of energy on a scale the world had never seen. Arriving in pieces from Los Alamos on July 12th, the gadget was handled with the utmost care. Plutonium, high explosives, and initiators were dangerous on their own, but together they represented the potential for untold destruction. Final assembly occurred in a makeshift structure known as the McDonald Ranch House, located 2 miles from Ground Zero. Scientists and technicians worked through the heat and dust, fitting the core together, connecting detonators, and checking circuits one last time. Armed guards stood at a distance while the team inside the ranch house performed their task in silence. On July 15th, the completed gadget was transported to the tower on a truck reinforced to bear its weight. Under moonlight and guarded by a security detail, the device was winched up and secured at the top of the tower. Final wiring was completed in the dark. Around the blast site, measuring devices were calibrated, copper coils were embedded into sand, and remote cameras were placed inside reinforced housings to capture the moment of detonation. In bunkers miles away, scientists installed instruments to record gamma rays, neutron bursts, and shockwave velocities. Security was tightened even further. The codename Trinity, suggested by Oppenheimer, likely inspired by John Donne's poetry, was used exclusively. Most of the personnel at the site still did not know exactly what would be tested. They were told only that it was a high-explosive experiment. Only a small inner circle led by Oppenheimer, Groves, Kistiakowsky, and a handful of senior scientists understood the full magnitude of what they were about to attempt. The original test was scheduled for 4 a.m. on July 16th, but a thunderstorm rolled through the desert, delaying the countdown. The team waited through the early morning hours, monitoring weather conditions and discussing worst-case scenarios. Some worried that the device might fail, producing only a fizzle and exposing the entire project to ridicule. Others feared it might work too well, igniting the atmosphere, unleashing an unstoppable chain reaction, or creating radioactive fallout that would drift far beyond the test zone. Despite the anxiety, no one turned back. As the storm passed and the skies cleared, final authorization was given. The countdown resumed at 5:10 a.m. Scientists and military observers took their places in bunkers, roughly 5 to 10 miles from the tower. Among them was Oppenheimer, who stood inside a reinforced shelter dubbed S1000, staring through protective lenses and shielding his face with welder's glass. Others lay prone on the desert floor, backs turned, their eyes shielded, waiting for the moment of ignition. At 5 hours 29 minutes and 45 seconds a.m., the gadget detonated. What followed defied imagination. The dark horizon lit up with an intensity beyond comprehension. A white-blue flash, brighter than the sun, illuminated the desert and cast shadows dozens of miles away. The tower, the steel scaffold holding the gadget, was instantly vaporized. A spherical fireball erupted into the air, expanding rapidly and sending out concentric shockwaves. The sand beneath the blast melted into greenish glass, later named trinitite. A towering mushroom cloud rose into the sky, turning orange, red, and black as it pulled dust and debris into the atmosphere. M. In the first seconds, there was only light. M. Then came the sound. The pressure wave hit the observation posts with a low-frequency roar, followed by a sharp blast and a rumble that seemed to shake the bones. Windows rattled. Sand jumped. The shockwave traveled for over 100 miles, shattering glass in nearby ranches and waking people in distant towns who had no idea what had happened. Birds fled into the sky. Animals froze or scattered. Some nearby civilians would later report seeing the flash and feeling the tremors, but would only learn years later what it had been. In the bunkers, there was stunned silence. The scientists and soldiers had anticipated a reaction. They had done the math, checked the circuits, calculated yields, but nothing had prepared them for what they saw. In those seconds after the blast, many were struck not just by awe, but by something deeper, an unease, a sense that the world had fundamentally changed. The test had succeeded. The gadget had worked. Mankind had split the atom, and the energy of the universe had been loosed. Oppenheimer, who had feared both failure and success, reportedly murmured lines from the Bhagavad Gita. "Now I am become death, the destroyer of worlds." The phrase would become synonymous with that moment, though others remembered him standing in silence, his eyes fixed on the receding cloud. General Groves, ever practical, immediately ordered secrecy reinforced and results compiled. The scientific teams collected data, retrieved film canisters, and analyzed blast gauges. The yield was estimated at 18 to 20 kilotons of TNT, twice the most optimistic predictions. The success of the Trinity test marked the beginning of a new era. Within hours, messengers departed to inform Washington. President Truman, at the Potsdam Conference in Germany, was briefed on the outcome. The decision to use the weapon in war, already under discussion, accelerated. The bomb was no longer theoretical. It was a tested, proven device. Soon after, assembly began on the uranium bomb, Little Boy, and the plutonium bomb, Fat Man. Their targets would be Japan. Back in New Mexico, the Trinity site was sealed off. Troops were instructed to minimize exposure to radioactive fallout. Most of the equipment near Ground Zero was destroyed or contaminated. Scientists returned to Los Alamos, where they reviewed footage, wrote reports, and quietly absorbed what they had done. There were no celebrations, no speeches, no applause, only a deep, collective awareness that the world before July 16th no longer existed. In the span of 10 seconds, the Manhattan Project had fulfilled its mission, and history had been rewritten in light and fire. When the scientists and military officers returned to Los Alamos after the successful Trinity test, the mood was neither triumphant nor celebratory. There was no cheering, no medals were handed out, no one raised a glass in jubilation. Instead, there was a strange, heavy quiet that settled across the mesa like dust. Something profound had happened, something irreversible. The bomb had worked precisely as they had hoped, and more powerfully than many had feared. But now, in the silence that followed, came the weight of realization. The mission they had labored over 4 years, often in secrecy and isolation, had reached its turning point. The device they built not only confirmed the theory of a chain reaction, it had introduced a new category of weapon to the world. The implications of this could not be confined to the desert where it was tested. The ripples had already begun to spread. Back in the laboratories and offices of Los Alamos, daily routines resumed, but a subtle change had occurred. Engineers checked circuits with greater urgency. Physicists compiled final reports and yield estimates, their handwriting a little more strained. Bomb casings were readied for shipment. The uranium-based Little Boy had already been shipped to Tinian Island in the Pacific. And now, the plutonium-based Fat Man, modeled on the Trinity design, was to follow. The endgame was in motion. At the same time, a current of ethical reckoning ran through the scientific community. For many of those involved, the test had shattered the psychological barrier that had separated their calculations from consequence. Up to this point, the bomb had been a concept, a problem to solve, an engineering challenge. Now, it was real, and soon it would be used. What that meant, what it could mean, was the subject of countless private conversations held in dormitories, mess halls, and quiet walks through the pine trees above the mesa. Some, like Niels Bohr, had long voiced concern about the implications of nuclear weapons. He had believed that the bomb's mere existence would change the political structure of the post-war world, possibly leading to a balance of power based on mutual threat. He had urged transparency, cooperation between nations, and the creation of international oversight. But Bohr's warnings were drowned out by the roar of urgency and wartime necessity. Now, his concerns echoed louder among his peers. Others, like Leo Szilard, took more direct steps. Szilard had been instrumental in warning the U.S. government about Germany's nuclear ambitions, but by mid-1945, he had begun to argue against the bomb's use on Japan. He helped circulate a petition signed by dozens of Manhattan Project scientists, urging President Truman to demonstrate the bomb's power before using it on civilians. They hoped that a non-lethal display might compel Japan to surrender without catastrophic loss of life. The petition never reached Truman. It was buried in the bureaucracy, quietly set aside by military leadership. Oppenheimer himself seemed caught in a whirlwind of emotion. In public, he fulfilled his role as scientific director with composed efficiency. He signed off on final reports, oversaw transfers, and attended planning meetings with the military. But privately, those who knew him best said he changed after Trinity. The fire, the light, the silence that followed. Something in him shifted. Friends noted that he became more withdrawn, contemplative, even mournful. When he was later asked what went through his mind during the explosion, he famously quoted from the Bhagavad Gita, "Now I am become death, the destroyer of worlds." It was not a boast, it was a lament. The bombings of Hiroshima and Nagasaki followed on August 5th and August 9th, 1945. Reports came back to Los Alamos in fragments at first. Casualty numbers, photographs of flattened cities, descriptions of firestorms and radiation sickness. The reality far surpassed what anyone had imagined. These were not military installations. These were cities filled with civilians, families, children. Some scientists wept, others refused to discuss it. A few tried to justify it, citing Pearl Harbor, the Pacific Campaign, and the prospect of a bloody invasion of Japan. Yet, even among those who had believed in the bomb's necessity, a sense of horror took root. They had created something that did not just end wars, it erased entire communities in seconds. The war ended shortly after. Japan surrendered, and the United States declared victory. Across the country, there were parades, banners, and joyous headlines. But at Los Alamos, the celebration was subdued. Many felt detached from the moment. Their work had succeeded beyond measure, but the cost could not be measured in yield or kilotons. It was etched in the silence of two cities that no longer stood. Soon after the bombings, the Manhattan Project began to dissolve. Scientists left Los Alamos and returned to academia or private industry. The secrecy lifted slowly, revealing to the public the scale and ambition of the endeavor. Most Americans were stunned to learn about the cities built in secret, the money spent, and the power that had been unlocked. Some viewed the bomb as a symbol of American ingenuity. Others feared what it signified, a future held hostage by weapons no one truly controlled. Oppenheimer met with President Truman in October 1945. The meeting was tense. Oppenheimer reportedly told the president he felt he had blood on his hands. Truman, uncomfortable and defensive, later dismissed Oppenheimer as a crybaby. It was the beginning of a rift between science and politics that would deepen in the years to come. The Cold War dawned not long after, and the bomb became a fixture of global tension. Other nations raced to develop their own nuclear arsenals. An entire doctrine mutually assured destruction, emerged from the ashes of Hiroshima and Nagasaki. The Manhattan Project had ended the Second World War, but it had also inaugurated a new kind of conflict, one fought not on battlefields, but in deterrence, policies, and standoffs. For those who had worked on the bomb, the legacy remained complicated. Some went on to advocate for arms control and nuclear disarmament. Others contributed to the development of even more powerful weapons, convinced that the only defense against annihilation was superiority. A few refused to speak about their work at all, burying the past under silence and memory. The Trinity test had shown what science could achieve when unbounded by precedent, but it had also revealed the price of that achievement. In the end, the question was not whether the bomb could be built, but whether humanity could live with what it had created. And that question, 75 years later, still echoes.
you.